To us about managing parallelism for tensor computations on GPUs.
So I'd like to thank the organizers for inviting me to speak here. So let me start with a slide on context and contrast, because I think this domain is quite different from, I think, most or all of the talks in this workshop. So I'll be talking about dense tensor computations on GPUs, and where these are key operations for deep learning. Matrix multiplication and convolution are examples of key operators. So most, maybe all of the talks in this workshop address irregular and sparse algorithms. So in this talk, I won't touch on sparsity at all. So with irregular algorithms, there are significant challenges to optimizing for parallelism that arise from the inherent irregularity and unpredictability of the computations. And so performance modeling is often quite abstract and may not really correlate that well with real performance because the modeling task is extremely hard. In contrast with dense tensor computations, first, parallelism is very regular and structured, and there is ample amount of inherent parallelism. So, so in terms of what are the challenges to managing parallelism, it's really, it's quite trivial to find a load balance distribution of independent work to all the cores, even with the massive number of cores on GPUs. Still, this is essentially a non-problem. So the main challenge is really managing and limiting data movement. So moving data from main memory to the processing units is orders of magnitude slower than actually performing the computations. And so the main focus of both hardware and software efforts, so essentially all of the architectural innovations from NVIDIA and other vendors, and various software efforts, be it at the compiler level or development of libraries, it's all really addressing the data movement bottleneck. And so performance modeling is still pretty challenging, but what I hope to show is that the kinds of modeling that's been done is actually practically useful in this context. So first, I just want to show a really contrived example. I use this in my introduction to high performance computing class because students who come in there, they don't realize how expensive data movement is. And so this is a synthetic example where we have a large 2D array, and this is there's an outer time loop, and then we're just going to run through the elements of the array, performing some contrived calculation that's a function of all of the loop indices so that the compiler doesn't optimize away the calculations. And so essentially, what this is doing is walking through the elements of the array one by one, performing that computation in the inner two loops. And then we're just going to repeat that a number of times. Now, it's easy to see that the computations are completely independent for each of the elements. And therefore, we could just permute the set of loops and then perform all of the computations for a particular element first. So essentially move the T loop inside. And so if I were to just compile this with the maximum level of optimization with GCC or Clang, it doesn't make much of a difference. So the version on the left takes 6.4 seconds, and the version on the right takes 0.26 seconds. And they're executing the same number of instructions. It's all because in one case, you're moving data from memory. The other case, it's just moved into a register. Question?
Is it possible that the innermost loop is optimized out by the compiler?
No, it can't be optimized out because actually there is a dependence. I mean, it doesn't actually do any. I mean, maybe you could come up with an algebraic closed form solution and optimize it out, but the compilers are not able to do that. Yes, question.
Is it just cache, or is it actually, is it this big enough that it's bigger than the cache?
I intentionally made it column-wise access here so that it actually, and it's a power of 2, so it just is missing in cache and going to main memory. So this is the worst possible situation. And that's why the difference, if it were coming from cache, the difference wouldn't be so dramatic. Right. Okay, so it turns out that compilers like GCC and Clang are extremely effective with all kinds of optimizations that essentially minimize the total number of instructions, but they're really not at all really effective in minimizing data movement. So even this simple example, neither compiler at the maximum level of optimization is able to do a transformation. So what needs to be done for optimizing data locality, the key transformations are really loop permutation, unrolling, tiling, etc. These transformations are well known, but how to do it most effectively is the challenge. So I want to just give an overview. Yes, question, Prashant.
In the last slide, is this conclusion also true if you're writing the code with like multiple threads? Is this conclusion between the
Sure, yeah. I mean, in this case, the parallelism is orthogonal. So essentially, you'll divide up in some fashion the array elements amongst the threads. But now it could be that if I have enough parallelism, the footprint is small enough that maybe it will actually get better because of the fact that it won't. If the total footprint can fit in cache, then it's going to speed up. Okay, so here we look at the basic form of code for matrix multiplication. We are performing a product of A times B to form C. And so if we take a particular element of C row I and column J, we need to perform the dot product of the corresponding row of the left matrix A and the corresponding column of the right matrix B. Right? So essentially, we have n squared output elements. As can be seen, the computation for each of the output elements is completely independent, no dependencies between them. And further, even within a single dot product, the multiplication operations can all be performed in parallel. So essentially, we have order n cubed parallelism with respect to the multiplications. The additions can't all be done simultaneously, but you can still get parallelism even in doing the reduction over a set of processes. So essentially, we have the point is the amount of parallelism is really ample and it's very structured, and so there's really no challenge in trying to do a load balance division of work amongst the number of available cores. So now, but let's look at the data movement issue. So now what I've done here is I've rewritten the same loop with the K loop outside. So all ways of permuting matrix multiplication will give exactly the same result. That's provable. But this gives us some insight into the data movement challenge. So now if we focus on a particular K, let's start with K equal to 0. Then we focus on what are the interaction between the data elements. So for A, if we fix K and we vary I, we run down the column. So each one of these elements needs to multiply with each one of the elements in a row of B, the same row of B, and the contributions are going to update every single element of the output. Okay, so you can see that there is a very significant many-to-many interaction that happens, and so therefore it's just impossible to reuse. So even if you have a fairly large cache, unless it is large enough to hold n squared elements, essentially it's with executing this loop with any of the permutations of this loop, we cannot avoid some multiple times that you access data elements from the memory. So essentially, we have ample parallelism, but optimizing for the movement of data is really the challenge. Okay, so now I want to first, for those that may not be familiar with this popular and really effective model that was invented at Berkeley by Dave Patterson and Sam Williams. It's called the roofline model, and it's really useful in doing asymptotic analysis with respect to bottlenecks, with respect to data movement. So let's consider first, in this case, a sequential single processor, and it may have registers, and it has maybe one or more levels of cache. And then we have main memory, where the data initially resides, and then final results will have to reside. And let's assume that there is some bandwidth, b bytes per second, that which data can be transferred from main memory to the processor. And let's assume that the maximum rate at which we can compute in the processor, if we have data in registers, is going to be c ops per second. And the ratio of c to b has essentially been going up over time. That is, computation flop rates have gotten higher and higher. Bandwidths are also getting higher, but not at the same rate. Right? So now let's consider some algorithm, some computation that executes a total of O operations. And in the process of executing the operations, let's say that the total of d bytes of data had to be moved between main memory and the processor. Okay? So now, so let's consider the two throughputs. We have a throughput rate, maximum possible throughput rate of c operations per second, and then there's a maximum rate at which data can be moved between the memory and the processor at b bytes per second. So if we have a total of O operations, we have to take at least O divided by c seconds to just perform the execution if we had everything in registers and never had to move anything. On the other side, the minimum time it takes to move all of the data that got moved in the execution of the algorithm, it should take at least d divided by b seconds to do that. So essentially, we can have a lower bound for the time to compute as the minimum of these two quantities, O divided by c and d divided by b. So looking at it in terms of throughput, essentially, which is the inverse with respect to time. So since we have a maximum of, so essentially we take the total number of operations that we have to perform, and we're going to divide that by the minimum possible time it could take to perform it. And so that's O divided by this max, and then we rewrite that by flipping it, and now it's going to be the min of the ratio of O divided by O by c and O divided by d divided by b. So essentially this, so now this term O divided by d, which is the total number of operations divided by the number of bytes of data that are moved from between memory and the processor, we're going to call it the operational intensity OI. Okay, so essentially this is, so the roofline model essentially captures the relationship between the achieved operational intensity in the execution of an algorithm, which is simply the ratio of the ops executed by the data moved between memory to the processor. And it relates that it sets an upper bound on the achievable performance. So essentially, the achievable performance cannot exceed both of these. So it's the lower of these two. And this term OI times B is visualized by having a sloping line where the intercept at operation intensity 1 is the memory bandwidth. And the point at which, and the horizontal line here is the peak performance or the computational rate of the system. So in this chart, we see the roof lines for 3 generations of NVIDIA GPUs, Volta 100, Ampere 100, and Hopper 100. And this has generally been the trend, that is, bandwidth has increased. The peak performance has also increased. But the critical operational intensity, which is the minimum operational intensity required for us not to be bottlenecked by the bandwidth, has also been shifting to the right. So, so any questions on the basics of the roofline model? Okay, so we can observe that in order to achieve peak performance, the achieved operational intensity in the execution of the algorithm must exceed the critical operational intensity for the system. Okay, so now I'll have a couple of slides on loop tiling, which is one of the most fundamental loop transformations in order to reduce the amount of data that we move from memory to the processor. And this is true for sequential or parallel execution. So with parallel execution, essentially the same ideas. The typical approach to parallel execution of dense tensor computations is to divide up the output space amongst the available threads, and then each thread is going to compute a subset of them. And so in computing its subset, it's going to have to minimize the data movement. So this slide illustrates what the idea behind loop tiling is. So here in this computation, we have loops running over this array, and the array is being accessed both column-wise and row-wise. And we're just adding up all the elements of the array multiplied by its transpose. And so irrespective of what loop orders we use, we are going to have one of them that's at a high stride of access. And therefore, we are likely to have a lot of cache misses. The basic idea behind tiling is instead of executing the loops in to the full extent with respect to each of the iterators, we're going to do this in a blocked fashion. That is so that we decrease the footprint of the data that we see, so that if we make this small enough, then reuses can happen in cache rather than go to memory. And the way that tiling is done is a two-step process. We split each of these loops by essentially these are strip mining of each of these loops. And then the loops are permuted so that essentially we have a set of loops that represent tile origins that are the outer loops. And then we have inner loops that go within the extent of each of these tiles. So for matrix multiplication, it's the same process. We have 3 loops. Each of these loops is split into a pair of strip mined loops, permuted, so that now we have 3 tile iterators and then 3 point iterators.
Is this something a compiler can do, or is
Yeah.
this something to do by hand?
So compilers can do it, but the current state of compilers is that often, and primarily because dependence analysis is too conservative often in real programs, the primary use of this is either through DSLs, where in this case the compilers will do it, or it is library writers who are manually writing it. Now, certain types of compilers, like polyhedral compilers, inherently, because of the representation of the programs, they can perform tiling too. Yes?
So this is assuming that you know what is the cache size of the machine, or like the hardware you're running on. So I assume this is maybe one reason why compilers may also not be able to do this automatically. But then is it possible to generate code that would run quickly no matter what the cache size is?
Well, that's, there are cache oblivious algorithms, but it turns out that cache obliviousness has a penalty. That is, if you know the size of the cache, you could actually prove that cache obliviousness is going to inhibit you from being able to achieve the best possible, because it goes recursively. Right? So, but the practical situation is that we do have machines that are long-lived on which the cache size stays fixed. So what I'll show at the end is that the performance modeling challenge, even for fixed cache sizes, I'll go through an analysis for one level, which is somewhat straightforward, to try to find what should be the tile size given a cache size or a scratchpad size to minimize the data movement. But once we go to the multi-level case, we have to do multiple levels of tiling in practice, then the problem becomes more challenging. And then further, an additional significant challenge is that just minimizing data volume doesn't just give you the best times, because there are latency effects. So what we are modeling here in minimizing data movement with tile sizes will just result in the lowest volume possible. But real architectures, there are significant latencies too. So if we had a pipeline where the number of computations you perform is asymptotically large, then the startups don't matter, the latencies, but that's not really true for many practically important sizes. So that's the reason why purely analytical modeling is still an open problem to be able to find the best set, and auto-tuning is really currently the most practically effective solution, and I have a few slides at the end on that. Okay, so now I'm going to go over how we can do analytical modeling if we had a single level of cache for which we want to find the optimal tile size. So this is tile matrix multiplication. I have a set of outer tile iterators, Ti, Tj, Tk, and these are symbolic or parametric tile sizes, Ti, capital Ti, Tj, Tk. Ni, Nj, and Nk are the extents of the problem. So we have these outer tiling loops, and then we have the point loops that go over the range of the tile size. And so you can see the indexing of the arrays is the tile origin plus the point iterator within the tile, right? So the problem we want to solve is what should be the values for capital Ti, capital Tj, capital Tk given some cache size. And here we will assume it's an idealized cache. That is, we don't have things like conflict misses and so on in this analysis. Now, if you were to actually use a software controlled scratchpad like a GPU, then this analysis is actually precise because there aren't any conflict misses then. So now let's so here we see a picture of the footprint with respect to each of the three arrays of the what is accessed within one tile. And so if we look at array C, since its index is only I and j, you'll see this is I and this is j, so that extent will be Ti times Tj. Similarly, B will have that footprint will have an extent Tk times Tj, and for A it will be Ti times Tk. And so to start with, for executing a single tile, we can attribute so as we assume that everything starts off in memory and we have to bring it into cache. So for A, it's going to be its footprint size, Ti Tk. For B, it's going to be Tj times Tk. For C, its volume is Ti times Tj. But I'm using a factor of 2 because as we iterate through the tiles, assuming that the matrices are large, since C is a read, modify, write, we bring it in and then we'll have to evict the contents from cache. So the volume of data that needs to move for C is going to be twice the footprint. So now what we'll do is just go inner to outer, performing a traversal. So as we run through each of the values of the k tile iterator, we are going to start moving with respect to the k direction with A and B, which explicitly index it. But since C does not explicitly index k, we are going to repeatedly access the same tile footprint for C. So we can model the total volume for traversing the entire tile k iterator. For C, nothing has changed because we have not changed the footprint in C. But for I and j, we basically have to multiply the initial value by the number of times we iterate, which is nk divided by tk. So essentially, we will form a cumulative expression, which is now 2 times Ti Tj plus Ti nk plus Tj nk. So essentially, in the same fashion, we can just proceed to through the j loop, where we are going to change tiles with respect. We will now change tiles in C and in B. Now, A's tiles are going to be the same as before, but we assume that we are going to use sufficiently large tiles to actually fully utilize the cache. Therefore, even though one tile could fit, this whole panel we assume is not going to fit. Therefore, we have to attribute repeater reload cost with respect to A. So essentially, this is the process that we can go through inner to outer, and then we can come up with an analytical expression of this form, which is a function of the problem sizes and the tile variable. And now, if we divide by the total number of FMA operations we perform, we get a more convenient expression for this. And so essentially, this is the function we want to optimize. So this is 2 divided by nk plus 1 over tj plus 1 over ti. Now, it turns out that there are many possible permutations of this loop. And then you could do a similar analysis for each one of them. And we could also use some techniques to prune based on expressions being algebraically provable to be greater than or equal to. So in this example, so the optimization problem is minimize this subject to the capacity constraint, which is that the sum of these tiles footprints is less than the cache size. And so this is a polynomial, and so essentially you could actually solve systems like this for specific values using a system like CVXPY. But you could also, in this case, it's easy to even to symbolically solve this. And the optimal solution will be that there is an expression, it's a little more complex, but essentially for all practical purposes, the optimal tiling is to have equal sizes for the tile size on I and j, and that's roughly equal to the cache size. And so one of the implications of this is we compute what is the data volume for this optimal tile size, and find what is the operational intensity for this optimal value. It essentially turns out to be the square root of the cache size. So this is an important result in that it says that the maximum operational intensity, and this relates to our roofline model, that is, your capacity has to be at least high enough that the operation intensity achievable through tiling can be greater than the critical operation intensity for that system.
NK is part of the input. You don't control that.
Oh, yeah. Okay. So I'm just so that's why it does appear, but we assume that nk is large. So 2 divided by nk is a very small value. So you could actually come up with an expression that does include the actual values, but it's not going to change that much. It's going to roughly, it'll change it slightly, but not very much compared to square root of cache size. All right. So this is an analysis that says if I were to do tiled execution, and then I look over, try to optimize over different possible tile values, what is the best operation intensity that I can get? Now, a question of interest is, well, is this as good as it can be, or maybe there's some other completely different way of performing the computation that might allow us to do even better? And so this is where there's been development of data movement lower bounds, and I'm going to go over a few slides on that. So essentially, computational complexity is much studied compared to data movement complexity. And so for those that aren't familiar with how data movement complexity is characterized, I'm going to go over a few slides using this simple example for the illustration. So this is a double-nested loop that's essentially doing a stencil calculation. And here we have a tiled version of it. And so if you were to look at the total complexity, it's and the number of operations does not change. However, what we are changing is the order in which we are performing the same set of operations here. So in the original version, we are executing it in this order. And as you can see, if we have, if this is much larger, let's say even a row is much larger than the cache, we're going to incur cache misses as we execute and then reuse the same elements as we go to the next row. And in the tiled execution, we have a smaller footprint, and so we might expect to see fewer cache misses. But the main point is that tiling does not change the number of operations, but reorders the schedule of execution. So for the base version, we might have, as a function of cache size, till it fits in cache, we have a larger number of cache misses, in contrast to the tiled code, where for a smaller cache size, the footprint fits in the cache, and so we see a reduction in the total number of misses. So the point I want to emphasize here is that we have two versions of the computation. They both have the same computational operation cost. However, the data movement cost is quite different for these two functionally equivalent versions. Now, second point is that even for the same code, the data movement cost is dependent upon system parameters, right? So this is quite odd compared to how we think in terms of computational complexity, whether we execute it sequentially or in parallel. If we execute the same set of operations, the cost in terms of how many operations we perform does not change. Is not dependent upon system parameters, whereas the data movement cost clearly is a function of a system characteristic, which is what is its cache size. So it shows that trying to capture the amount of required data, we might be interested in this question of what's the minimum possible data movement for executing a particular computation. And so it's a non-trivial question to answer, because it can change not only for different forms of equivalent forms of the computation, but also dependent upon the parameters of the system on which it executes. So I guess so in this particular version, we might say we can try all possible tile sizes or block sizes and come up with a minimum. But then how do we know that that's the lowest possible? Maybe there's some completely different form of execution of the set of operations that satisfy all of the dependencies. That could be even better. So this is really the problem that the data movement complexity question asks. What is the lowest achievable data movement cost among all possible equivalent versions of a computation? So by equivalent means it needs to produce the same result. So this is a question that was addressed by Hong and Kung in their classic 81 paper red-blue pebble game. And so the way that they addressed it is to use this abstraction for a computation, the CDAG, or the computational directed acyclic graph, which you can think of as explicitly conceptually enumerating every operation that's performed in the computation, and having the producer of the values that are consumed in an instruction have an explicit edge, and initial inputs also have vertices and edges. So the significant benefit of this is now these two versions of the program have exactly the same CDAG. So you can reason about all possible equivalent forms by just reasoning about all possible valid schedules of execution of the given CDAG. Okay. So they formalized this in terms of a pebble game, which has two types of pebbles, an infinite number of blue pebbles, which essentially represent values that are in slow memory. So this is modeling the complexity of data movement in an abstract way for a one-level memory hierarchy. So the red pebbles represent values that you might hold, say, in registers or in fast memory. And so there are a finite number of the red pebbles that correspond to your capacity of fast memory. So you start with an initial state where all the inputs to the CDAG, these black vertices, have blue pebbles on them. That means there are initial values, but they are sitting in memory. And then the final state, all the specified output vertices must have blue pebbles, which means we have computed the result successfully and placed it in our permanent memory. So there are 4 rules in this game. So the first rule says if a vertex has a blue pebble on it, then we can place a red pebble on it. if we happen to have a red pebble available, we can place it on it, which basically corresponds to, we're going to load that value from memory into fast memory, let's say registers. So the reverse is, if I have a red pebble on a vertex, we can place a blue pebble on top of it. That is, we can place both pebbles on that vertex. That basically corresponds to, I'm storing the value to memory, and I'm also retaining it in the register. Now, I could, of course, there's a R4 which says red pebble can move from any vertex holding one. So after we have saved the thing, we could also remove it, right? And then there is a rule for computation. The firing rule says, if all predecessors of a vertex have red pebbles, then we can place a red pebble on that vertex. That says I can compute because I have its operands in fast memory, right? So essentially, the data movement complexity of an algorithm is the minimum number of invocations of rule 1 and rule 2 for any valid game. So essentially, this is the way that the data movement complexity was formalized. Now, of course, this still doesn't give us a practical way of finding it, because there are an exponential number of schedules. But then they developed a method to essentially come up with a way of asymptotically bounding the data movement complexity for certain structured CDAGs. So now, so what do we? When can we know what the exact data movement complexity is? When essentially we develop lower bounds, and then we develop some actual upper bounds through a concrete schedule like a tiled execution. And if these two match, then indeed we have a tight bound for the computation. And it turns out that for matrix multiplication, tight bounds are known. So the initial work of Hong and Kung only gave asymptotic complexity of order n cubed divided by square root of c. And then successively, later works essentially refined the constant and made it 2, so that we now have a lower bound from the lower bounds arguments of 2n cubed divided by square root of c, which gives us an operation intensity upper bound of square root of c. So essentially, we see that the 2n cubed divided by the square root of c was what we achieved through the tiling scheme that we optimized for one-level cache. So essentially, because of the progressive refinements with respect to the lower bound on matrix multiplication, we do have a tight bound that we know that what's the absolute minimum data movement that we need to move for matrix multiplication, and that is actually achievable. So so there's been a lot of work by Jim's group on doing all other, lower bounds for various other linear algebra computations and even larger classes of computations. So yeah, I'm going to pause here if there are any questions with respect to this lower bounding argument before I continue.
Are there lower bounds where you look at the bisection, where you count and look at how much data has to cross various cuts? Is that?
No, this is actually there are a few different techniques, but with respect to these linear algebra computations, it's using essentially the Loomis-Whitney inequality or the generalizations of that is the basis for the arguments. It's
and there are extensions to parallel cases. That's what you're.
Oh, maybe that's what I'm thinking about, right? Like, yeah.
yes.
There's like mixed precision matrix multiplication where maybe your operands inputs are in int 8 and then the outputs are in int 32, or do we also capture this class of?
So I think that issue is a little orthogonal to the data movement question. That is, of course, if you do things in mixed precision, you'll need to use scaling with respect to what data is actually being moved, and if accumulations have to be done in a higher precision, it's an interesting question. So
there's a literature on that.
So Jim, are there complexity results with respect to lower bounds?
You can tune the size of each array, for sure.
And lower bounds are known for?
Yeah, they show up in constants.
Okay, thank you. Question?
You mentioned the red-blue game is a good model for single layer cache system, and I'm just kind of curious. So, like, what would the generalizations of this? For
So the
multi-level
generalization to multi-level is pretty straightforward. Actually, it's the same technique that is applied to multi-level caches. In terms of each level, it's going to just depend upon the capacity at that level. So, the real challenge with respect to so essentially the tight bounds with respect to what will minimize volume at a given level is really known, but that's not sufficiently good enough to analytically figure out what should be the multi-level tile and distribution in a parallel like on a GPU that will give you the minimum. Was there a question?
So like one thing with cache abilities is that it can generalize to any levels of hierarchy, like with changing sizes and all. And in this case, when you have multiple languages,
So I think that's the challenge is really if you know all the cache sizes, you're better off doing auto tuning. I can go over this offline, but if you go with the cache oblivious approach, you're constraining the schedules, and therefore it's actually provable that you can do better by a constant factor by being non-cache oblivious with respect to the.
And there's also the Bliss approach, where the vendor supplies a optimized core just for the innermost loops, and then the software optimizes all the tiling around that. And that's done in practice.
Okay, so I want to just give one example of where the modeling with the roofline model is it kind of matches architectural developments from NVIDIA. So what I show here is for 3 generations, what's the capacity of the shared memory. So a GPU is organized as a set of multiprocessors. Each multiprocessor has some amount of shared memory, and all of the threads within that streaming multiprocessor can share that. But between the SMs, there is no sharing possible. That's the model of the GPU. So therefore, the maximum operational intensity achievable with respect to data movement from the main memory is really constrained by the square root of the amount of shared memory per SM. And so so this is basically that number for FP16. What is the achievable square root of the cache size with this data type? That's 221. And the critical OI for this machine was 136, so there was a margin of 1.6. Then the more recent development of the Ampere, the increased amount of shared memory, and therefore the operational intensity also went up. The critical OI went up. The margin went down slightly to 1.44. With the Hopper, we see that the shared memory went up slightly. The operation intensity upper bound went up, but however, the critical, so essentially the margin right now dropped. However, what they did with the Hopper is they now enabled clusters of up to 8 of the SMs to essentially share the data amongst themselves. So in effect, it was an architectural technique to increase the amount of, effectively the total square root of C essentially that is as big a tile that can be collectively operated upon by a cluster of SMs. Now, the best would be to actually use the ability to share across the entire on-chip memory, which is what spatial accelerators and systems like the Cerebras do, but that requires a programming model that is much more complicated. Okay, and so this is a very ingenious way of staying with the very effective software model that has worked with NVIDIA, but then incrementally increasing it so that we address fundamental data movement constraints through architectural innovation that is able to keep essentially the programming model almost the same as before. Okay, so So I've talked about analytical minimization of data movement, talked about it from the point of view of upper bounds and lower bounds. And so the strength of analytical modeling of data movement is that these analytical expressions can be automatically generated for, not for just for matrix multiplication, but for any affine computation. And so in work in collaboration led by Fabrice Rastello's group in India, tools developed that can automatically derive symbolic I/O, essentially this data movement complexity bounds for affine programs. Now the minimization problem, which is now coming at it from the upper bound side, that is, can we find these optimal tile sizes to minimize data movement? So this is essentially a geometric program, and efficient solution is possible using convex solvers like CVXPY. And so effectiveness in this kind of an approach for optimizing CNNs on multi-core CPUs was demonstrated by some earlier work by us. However, when it comes to GPUs, things are somewhat more complex, and one of the key challenges is just minimizing data volume is insufficient, because with GPUs, they use massive parallelism as a mechanism for tolerating latency. And therefore, there's a trade-off between data volume and latency tolerance via the parallelism. So minimizing data volume requires higher register and shared memory use per SM. But then this reduces the amount of concurrency, so therefore it suffers from pipeline stalls to latency. So this is the kind of effect. With CPUs, it's much more coarse-grained parallelization, and therefore the analytical modeling was somewhat sufficient to be able to find very good solutions. Whereas with GPUs, it really is still an open problem to come up with an analytical modeling approach that essentially will incorporate all of these trade-offs with the latency versus concurrency trade-off and the data movement minimization. And so currently the most successful approach for GPUs is really auto-tuning compilers. So I'm going to use a few slides now to explain how that works, and then we'll wrap up and maybe have a few minutes for discussion. So I'll give the example of TVM, which is one of the effective auto-tuning compiler systems. And so what an auto-tuning compiler does is it takes a high-level expression of a computation and generates essentially a search space for essentially multi-level tiled execution. So here is an example of the kind of schema that's generated, where we have, this is matmult expressed as an abstract expression. And what the schema generates is a multi-level tiled code with some number of levels of tiling for each parallel loop. In this case, I and j are parallel loops. And then for each reduction loop, some. So these are somewhat parameterizable, but there's a schema that it uses to generate this. And then, we therefore have a set of variable tile sizes that are unknown that have to be found. So essentially, the optimization problem is really a search problem in a space, in a large space, with lots of possible combinations of tile sizes. And we want to find that combination that gives the fastest execution. So what is done is to use a dynamically generated machine learning model for it to guide the search, and I'll show a little more detail in the next couple of slides. So it generates a feature vector that is automatically extracted from the code structures, and it uses various features from the code structure. It deduces things like what would be the size of the footprints with respect to the access to the memory, what are the extents of loops, and so on. And then so essentially we have this process here. We have an input operator specification. Let's say we want to perform matmult with sizes 256, 128, and 64. So all of this works for a specific size of problem, so this is not symbolic, and this is quite useful in many machine learning pipelines where the operators are of size that is known, and they don't change during execution. So then we have a search space construction. So the search space is essentially a set of possible points where each point has a feature vector that encodes that point, and that's derived from the tile size vector. So corresponding to a particular tile size vector, the feature vector is constructed, and that's the search space. And it's so this is pretty large. Often it's hundreds of thousands to millions of candidates. And so there is an iterative process of initially start with some random configurations, and then actually generate code, execute it, measure it on the target platform, and then create a training database of instances that were actually executed, and that refines the machine learning cost model. And then the machine learning cost model is used to guide this search for future candidates. So essentially, that's the approach, and you can see it's quite effective. So these are examples for ResNet, and this I've shown a few of the cases where I found the biggest difference between CUDNN, which is a highly tuned vendor library performance, to what is found by the auto-tuning compiler. Now, I mean, we need to be clear that this is apples versus oranges in the sense of CUDNN is a general purpose library. It's intended to perform convolutions for an arbitrary size that is unknown. And so internally, it has some number of kernel versions and some kind of a selection strategy. But that's, whereas with TVM, for that particular shape of the operator, it does extensive searching to come up with something that works better than what CUDNN's implementation does. Okay, so to summarize, yes?
Did you try, like, if you did this by hand carefully, like you were doing with the other, could you beat Answer by?
No, it's just a big search space, right? I mean, I'm not aware of anybody who has an analytical approach that can figure out the multi-level tile parameters, what should be the shapes of the various GPU groups, the thread blocks, and the register tile sizes to find something that actually does better than what. Yes.
So this is happening offline. Like, what
This is offline, yes.
What if I give you a weird problem size online, and then can you just in time compile like a kernel for my problem size and make it faster?
I'm not aware of anything that successfully does that. Yeah. So this is really suitable for machine learning pipelines which have fixed shapes, and it's really effective for that. But for I don't believe there's any effective solution for. I mean, there are many systems that do some JIT, but I don't think any of them have demonstrated real effectiveness. Yes.
I mean, actually, kind of just on that question, like, is there any way of getting much more quickly, like some sort of like very close approximation that could work across the different?
I mean, there are systems that do limited auto-tuning, so they are that's so far. There are libraries which have been engineered by expert developers who create certain number of versions and some kind of a decision process. And but again, I don't believe there's anything that has anything that's dynamic and quick with respect to. I mean, there are a few efforts that have extended the auto-tuners for limited dynamic shapes. That is, for example, in many situations, the number of tokens may be variable, but the other shapes are fixed. And so there's been some success with that, but that still involves an offline phase, and then there's some modeling. So in those, some combination of analytical modeling plus some offline work has been effective. Okay, to summarize tensor computations on GPUs, there's ample and regular structure of available parallelism. Maximizing parallel performance is essentially equivalent to minimizing data movement overheads. So performance modeling efforts have not been perfect, but they have often been useful in practical performance optimization. So a question I'd like to end with is, for irregular parallel algorithms, can modeling be effective? So the model doesn't have to have a perfect accuracy with respect to prediction, but should have discriminatory power. And this is the question that essentially, given two alternative choices A and B, can the model predict which will execute faster at least 50% of the time? If so, then at least it's a step towards modeling. So it seems like this is something that's extremely challenging in the irregular world. And so I guess this is maybe a question for discussion. I mean, are there situations in the irregular space where there are some predictive models that satisfy this criterion, that is better than random? That is, and how much more? I mean, can we get 80%, 90% of the time that? So if you look at the model that TVM uses, it's not a perfect model. That's dynamically built model, but it turns out that it is more than 80% accurate with respect to, if you take two random cases and say which one is going to be faster after it's been trained over maybe about a few hundred samples, it turns out that the features are pretty effective in especially in discriminating really bad configurations. It may not be so good in discriminating between very good and very, very good, but it's really very effective in discriminating between pretty good, good or versus not good. Okay, guess we have some time for discussion. Thank you.
Any time for questions, discussion?
Please.
So part of the design space for matrix multiply and other algorithms involves replicating the data to reduce communication. Does that fit? Is that used in any of the tools you mentioned?
No, that's a good question. So, are there some solutions now for?
Yeah, I gave a talk in the other Simon's program a couple of weeks ago on this. So
I see that. Thank you.
it's all
Yeah.
posted there.
I see. Great.
Does that work on GPUs too? The
Well,
replication?
it's if you want to replicate across different parallel units. So if you have multiple GPUs, then yes, it would make sense.
So would that fit into the learning model? I mean, could you get your learning model to somehow
Well, I mean,
include that in the design
the
space?
particular
and-
learning model that's currently being used may not, but with learning models, you could always make it learn. Right? So there's always scope for improving on and adding more features. So essentially, this would be, you need to have additional features that says replicate or not. Yes, separate.
Is there any support for irregular computation if you make it somewhat structured, not perfectly dense, but define structures in irregular computation? Can current compiler frameworks find the structures and try to optimize them?
Well, there are some efforts on that, but it's pretty challenging. I know that Louis Noel, for example, he has some Louis Noel Pouchet at Colorado State. He has some work where what they try to do is to, but again, this will involve some, you can call it start time analysis. So you have a sparse matrix. You look at the structure and then try to encode that in terms of some regular patterns with some zero fills, right? But it will require a specialized analysis.
The file sizes would vary depending on the sparse.
Yes, they will vary.
Or even irregular like a matrix one.
Well, I mean, that's still, you could still get good performance if you have a collection of dense blocks. I mean, this is the kind of stuff that was done way back with OSCI, and there are, I think there are several research efforts, but I don't know if there's anything that really is being used in production where its performance is better than other alternatives that are using sparse representations.
There's a sparse plots committee that is meeting weekly to try to come up with an interface to sort of hide all these optimizations that different vendors are doing in a common interface. So there's a lot of optimization to be done.
So with irregular ones, like how do you design the trade-offs between compute and data movement there? Like, is there a known thing already there to?
So I guess with tensor computations, the reuse directions in the sparse iteration space are the same for dense and sparse. So you can extend techniques from dense computations to the sparse in terms of tiling and so on, right? However, the dependence on the sparsity pattern has to be, there has to be some kind of pre-characterization on a per tensor basis, which could possibly be fast and then reused across. But I think these are pretty open problems.
Do you ever, I mean, we've heard a lot of talks about energy also, like, and I know that data movement is the biggest user of energy, so by minimizing data movement, you are minimizing energy, but do you ever consider more fine-grained models of energy usage into?
I myself have not. There have been some works that have, but I think in general, data movement minimization is really required for energy minimization. Now, there are some other dimensions, such as if you want to reduce voltage, for example, to slow things down. That's a different kind of a direction that is also could be used to reduce energy but make it slower. So, but reducing data movement both helps with speeding things up as well as with reducing energy.
So just in response to that, the algorithm I mentioned that replicates data to make matrix multiply go faster can actually achieve perfect strong scaling in energy, so that if you double the number of processors, you're running and so you burn twice as much power, but they'll run exactly half as long, and so you use exactly half as much energy. So, and there's sort of a model, which of course is approximate, but to prove that.
Interesting. Thank you.
But then are you also taking into account the cost of piling up more like memory banks?
Yeah, that's in the model.
Question over there.
It seemed like in your red, blue, pebble game, you were counting the cost of putting something into fast memory, but these were maybe being measured as kind of individual addresses or locations. But in your actual modeling, do you need to think about cache lines, or what's the right units to swap?
So the basic model is not modeling cache lines, but you could extend them to model some spatial locality. So essentially, you then have to reason in terms of units that are collections of elements.
But this is not being used in production systems?
So I don't believe, so the main benefit of the lower bounds analysis is to give us confidence that our upper bounds are really as good as you can get. And so the actual techniques that are used to optimize are all, they're exploiting vectorization, for example, and so they do handle spatial locality.
Any idea on how CPUs and GPUs are different fundamentally in this way of thinking about communication?
So what is common with both is that you want to reduce the volume of data, movements in the memory hierarchy. But where they are different is that with CPUs, we do not, so latency effects are not as significant because you rely upon caching and coarse-grained parallelization. Whereas with GPUs, the parallelization is very fine-grained. And the GPU model inherently relies upon very, very fine-grained zero cycles switching between lots and lots of threads that are active in order to be able to tolerate the latencies of memory access. So essentially, to find the optimal configurations on GPUs, you have to also account for the latency in the modeling, which is a challenge. Whereas with CPUs, you can have pretty good solutions where you're not explicitly modeling latency, but just doing tile size optimization to minimize the volume of movement.
Any other questions? All right, let's thank the speaker again. Thank you.
Thank you.
We'll resume at 10:45. There should be food out there, although it might not come till 10:15. I'm not sure.